Will? Okay, people. I've got the new radio microphone on now, so it's an amazing sense of freedom. Hopefully the clarity will be a lot better as well. Strange walking around without a lead, which I've been doing for years, and hearing the microphone working. I can hear it. Strange feeling. Okay. A lot of things have happened in terms of announcements. The two most important first order announcements are, of course, the quiz, the date, being Friday the 5th of July. I'm getting confused with the submission time for the assignment. 5th week in any case, and the assignment, which is the end of the 4th week. Now, there are problems with the assignment, which I'd like to talk about a bit as part of the lecture today. In the input-output, which was supposed to be last Thursday, but I opened it up immediately so you could spend time reading it and maybe you can get something out of it. None of this material is presented, this lecture material is presented in any way with the thoughts of the assignment, by the way. It's completely independent. So it's not necessarily true that you'll find, in some sense, ways of doing the assignment out of the material there, and you may have to do other work. The problem being, of course, I can't know how much you do and don't know, how much C you do and don't know, and I don't want to give a course in C. It's just too detailed, it's too boring for 50% of the course. So you will need to do your own work to some degree. And the only thing I can suggest to you is, 1, use the forum, 2, use the labs. If you vote with your feet in the labs, I'll put on another lab. Okay, but I want you to overload Kevin. You overload him, you'll get more lab. The consultation this afternoon I tried between 2 and 4, see how it go. Only a few people turned up. It was a try. I decided not to change it just yet. Next week I'll probably put it on Thursday. I have to check the timetable, see when I can get a room. Not happy with doing it next week, so close to the end of the assignment, so I'll try to get one on this Thursday as well. So that will be my next consultation, where you can ask me questions about the assignment. Before I start looking at slides, and you do, let's talk about that just a little bit. I don't, in one sense, want to tell you how to do it, although I think, having talked to a few people now, I need to talk to the 50% of the people here that have very little experience with C. And the first thing I would say is, don't lose sight of what the essence of the problem is, and that is parity. Parity of the two boards. So don't get hung up. All these don'ts. I hate these don'ts. It's really what you do, not what you don't in a sense, but you will get hung up with input-output. And I've got a whole lecture on input-output, a lot of it which is irrelevant to the assignment. So in a sense it makes it worse for you. Forget the input-output completely. Write a program with no input-output. No ADT. There's my 2-hour lecture. It's gone straight away. No input-output, no ADT. That's all I'm going to be talking about tonight. Just write a simple little program that has 2 arrays, one called start, one called goal, with exactly the right configurations, and write a simple little function which calculates the parity of the two. And if the parity is the same, the goal is reachable from the start. If it's not the same, it's not reachable, hence unsolvable. That shouldn't take you more than about 40 lines of code. You could possibly do that in an hour. If you're really, what we call worried, concerned, submit it even. You've got then a placeholder. It's at least solving the problem of the parity of two boards. Okay, now, you've done that in any case. Now you get into the dressing, if you want to call it, the window dressing. Get the input-output right. The input, obviously, is can you read from standard input? And how do you do that? First, assume no errors in the input. Just read a string of characters and see if you can convert it. Don't do any error handling. It'll occupy you completely. You don't want to do that. You just want to get it working for what is correct. You get that working, you can then think, well, what happens if the B is not there? And you could put a little bit in there if you feel like it, kind of thing. Or you can think, well, if that's not there, maybe I should flag that. And the error will happen quite naturally as part of the programming, because you'll have an if statement. And you'll say, oh my goodness, there's an A where there's a character there, it's not a B and it's not a digit. If it's not a B and it's not a digit, it's probably wrong. I should report that and do a print. Okay, a lot of it's quite natural. Let it come naturally in some sense by starting with something that works. Two arrays, do the function. Your function that calculates parity will not change from beginning to end, ADT or no ADT. It's the essence of the problem. So start simple, 40 lines of code, and then embellish. Do the standard input-output, do the error detection, and what I did was the last thing and of course the error detection is number 2. Number 3 is how do you do it without using any arrays, which you've still got them in the program. I would almost defy anybody in this course, no matter how good you are, to write the program without using an array in the first instance. It's almost, I would consider, impossible. It's you've got to be one hell of a programmer to do that, and obviously shouldn't be, and you obviously shouldn't be in this course. You need to start with something fixed, get the logic right, because the process of going from an array to no array is quite straightforward. Once you've thought of how you could do it. There are a couple of ways you can do it. It's much easier doing it once you've got a working program. That's checking the input, checking the output, or putting the right output. You've got the right amount of errors in there. It's all working fine. And you say, well, now, can I get rid of all of these arrays? And a couple of arrays I used in the first instance, and I got rid of them one by one. See how you go. When you get rid of one, that worked quite well, then maybe I'll use it over here too. So let that grow. Don't go straight off to a program that reads the input, generates the error messages, has no arrays, and is an ADT. You're crazy. No one can do that. I can't. I wouldn't be able to do that. You start with something and let it grow naturally. Okay, as things are solved, you go on to the next step. So start as simple as possible, and what you think is the next best thing to do. I personally found that making the ADT last, I made it, when it was all finished, I said, well, it's a nice program, it's a bit messy. Gee whiz, it's all over. No, I think I can clean that up. You know what, I'll make an ADT out of it. It wasn't even the initial design. And I found that in an hour I had to convert it into an ADT. It was quite simple. And it just cleaned it all up a bit. So it was really just a tidying up process. It wasn't the driver. It shouldn't be your driver. And particularly when you've only got 30 or 40 lines of code, having an ADT means you're mucking around with 3 files. You're already giving yourself a headache with 3 files. You've got the header file, you've got the implementation, and you've got the main program. And you're all over the place. You think, oh, well, I'll put that there, over there. It's complicated unnecessarily. If you had 400 lines to start off with, okay, you've got to organise it. You go crazy otherwise. So the craziness works the other way. When it's small, don't have all these files. Just one file where you edit and you've got everything together. When you've got it all working, you then say, wow, it's a bit long. I think I'll break it up into a couple of usable bits and pieces, which I know. And the ADT becomes really fine then, because then you say, well, I'll put all this detailed stuff on the board in that program over there, in that implementation of the ADT, and I'll get the main program over here, because it's different. It doesn't need to know an awful lot of things. So you then separate. Then it's convenient. It's convenient to have an ADT when you've got complexity. When you force it on a very simple program, it's a pain. Okay, so I hope that helps a little bit. Start simple and grow. I deliberately haven't put out any marking scheme to now, for the reason if I say, well, if you do have this or don't have that, you get so many marks or you lose so many marks. People then all will come back to me on the forum, well, what happens if I haven't implemented something else? And you get all these questions about specific things. There is just one assignment and it's worth so many marks. Now, I will come out in the next few days and actually say what the bottom line is. I think that's the most important thing, what you sort of have to have in the assignment, really, to expect a pass. And after that, it'll be improving marks. And just personally, I haven't actually thought it through yet. I haven't used this assignment before. Personally, as long as you've got the essence of the problem, which is the parity checker, reading input, if you read all the test cases that you can think of, that means good and bad boards, you get them all right, and you're reading input, even if you've got arrays in there and it's not an ADT, I'm inclined to give you a pass. Okay, an ADT doesn't give you, it's not, if you haven't got an ADT, you were 0. No way. Particularly when it's not even much work, it's an hour's work. Okay, so if it's costing you extra time to do the ADT now, get rid of it and just have one program. I've got two versions, one program and an ADT version, which is a bit of a nuisance because I've got to keep both of them up to date. So I should throw away the single program, but I like it. It's sort of easy. Just one program, everything's there. 200 lines roughly is what my single program is, if that helps you. And that's manageable. If it was 300 lines, I'd be hesitating, and I'd say, well, no, it's too big now. Really do have to keep on the breakdown to an ADT. So I hope that helps you just a little bit. So if you go up to the top right here, you see the upcoming due dates, you see the assignment, and you'll see at the top there the make submission. I can't easily test that because I'm not a student, so I don't have the statuses or the privileges that you do and don't. So I'm sure I'll hear on the forum or somewhere if it doesn't work, somebody tries it and it doesn't work, so let me know, I'm sure you will. Last I looked, nobody had submitted yet. You can submit as many times as you like, of course. I don't know with check submission and collect submission whether they'll ever work in the sense that I will go to all that trouble because it's a lot of work to put all the feedback in and to get it all organised so that you can collect it. I don't know how we'll handle that. At this stage, my focus will be on 350, marking 350 assignments. Okay, that's the assignment. The midterm exam is absolutely compulsory, 1. 2, it is absolutely an internal online examination. You will not have any IDEs. You will have virtually nothing. You'll have a very restricted environment. You'll have an editor. You'll have a compiler. And you'll have your brains. Okay? You won't have your home computer. You won't have your own laptop. You won't have your own compiler. So you'll need to use an editor if you don't use some kind of editor, a simple editor. If you haven't used one before or you haven't learned one, you'll be in strife. You've got to sit on the CSE's network at some point and just practice a bit with gedit or something that you can make simple, write a simple program and get used to the compiler and the errors. Okay, you need to spend some time on the school's network. The quiz will be very much a practice for the final. I have not been allowed, I've asked whether I can have a proper practice and it's not possible. See this quiz, the mid-session, as a practice for the final. It'll be exactly the same for the final. I'd love to give you the same seating allocation. I'll talk to Mei Cheng about that and see if that's possible. Just so that you know where you're going and what you've got to do. Okay, basically every computer in the lab has been booked for that Friday night. So it's a big thing for the school. All right, are there any questions about either? Okay, you can always throw the questions at Harrison. I've tried to answer some of the questions on the forum, but every time I see a question, Harrison's already been in there, and I haven't seen him make a mistake yet. So he's very good, and he certainly spends a lot of time behind the machine, answering your questions. All right, input-output. I have changed some of the earlier slides. Do I want to address that now? Do I want to even think about it? What were the earlier slides again? I did change something in revision, but I can't remember what it was, but it's not really relevant. It's more for the future. Memory allocation. Let's just go straight on to, otherwise I'll lose too much time. Okay, just the I/O culture on C, in C. There are basically three places where you read and write data. That's command line, standard in, standard out, and files. Last time I gave this kind of course, files were never used. Files are irrelevant because standard in is a file, standard out is also a file. You actually, printf that you have already used a few times is actually syntactic sugar. It actually is fprintf, I say that somewhere in the slides. Fprintf, one word, is what the correct C library call is. And an fprintf has the first argument is the file that prints to. And that is standard out when you just want the screen. So every time you do printf and then some kind of string, Fred, you're actually saying fprintf bracket standard out, comma, and then the string. Okay, that's the real instruction that you're actually, or the real library call that you're making. So the standard in and standard out are really just files, and they are more than sufficient for the I/O we're doing in this course. But sometimes some people like to open and close files, and you'll see why I'm not real keen on them from a teaching point of view in a moment. The command line is very popular in C, and that's something that is sort of idiosyncratic in C. C is not the kind, or Unix I should say, is not the kind of language where you prompt the user for information. Whenever I see the user ask for, please input something, I always think of Microsoft. It's always great, a little bit to me. The Unix style is command line arguments, where you do a man on the command and you see what your options are. Minus A does this, minus B does that, minus being it's an optional argument on the command line. So you have a whole series of options, and you as a user says, well, I want the minus C and the minus F, and after the minus F comes a file name, and after the minus Z comes something, and minus O is optimization, I want level 3. So you have this whole long, dirty long big command line with all these options. That's in a sense the same as please type in, which is what Microsoft people do. Unix tends to be command line driven, so the command line is important, and processing a command line is important. The advantage of that is, well, I'm running too far ahead there. You'll see why prompting the user for input is a bit of a nuisance. So here I've got a little program which just reads from the command line. I won't go into any detail in it. The only thing that's really important is it's a scanf, it's an scanf, which means it's a string scanf. SS scanf. Okay? Double S. The first S means string. And it's reading, that means its first argument is going to be a string. First argument of an scanf is a string. And the string is argv1 in this case. That is a string because it's a two-dimensional array. The start of that string is argv1. There's also a string at argv0. That's the name of the program. The character string starting with ./d, a dot, or name your program. If you're not using a ./ you just call it puzzle. It'll be a P. UZZLE. That'll be the string, argv0. argv1 is going to be the first argument on the command line. argv2 is the second argument, string. It's a double array, two-dimensional array. Okay, that's why it's an argv1. That's the only thing that's really important. So when you take argv1, you read that string, scanf will convert it to a decimal number, because it's %d, and it wants the address of the place it's got to put it, the address of num. All the rest is a bit irrelevant. That's the really important thing. Two other things, sort of on the boundary of that, is we first check that argc is at least 2, is not less than 2, at least 2, because if it's 1 means that there's only one argument, and that is the name of the calling program. Remember, argc is always one more than or one less than what you think it is. Argc is the count of actually how many on the command line. So if you've got argc is just 1, then argv1 is undefined. Argc being 1 is just argv0. Argc is 2 means there's an argv1. If argc is 3, then argv2 is defined. If argc is 4, if argc is 12, then argv11 and 10 and 9, they're all defined. They are all that argument string from the command line. So that argc is very important to make sure you don't get a segmentation violation. The only other thing that's important is I am checking that what the scanf returns, the scanf returns, is in this case at least one thing, one element. The one thing it's returning is the reading of the %d. If that's successful, then it returns 1. If there are 2 %ds in there, if that string had 2 numbers embedded, then it would read 2 things, and the scanf would return 2, the number 2, numerical 2. Okay, so I'm doing a couple of things on that one line. I'm not only reading, I'm checking that I have read, and I'm making sure it exists, first off. So there's my little count program. And here's it working. I compile it, and it creates an A dot out. I keep it, oh no I have. I know why I've done it, because count C I've called it. I hope I was consistent with the actual name, count C. I've called it count C because I actually want to use that and differentiate it with another executable later. So now I've got to see the prompt is wrong there. That should be /count C. And if I just type in /count C, sorry, the typo, then it says, well, there are no arguments, and that program will come up with the usage. That's what I told it to do. If you've forgotten already or didn't notice, I hope I did that. Yes, I did. Yes. See, the fprintf comes out if there's a problem. Number is defined here. Printf usage. What am I doing? Usage %f integer. If it's less than 2, then it's 1. There's no argument, and therefore I've got to do the printf. Okay, so I've broken the condition, therefore I'll hit the printf. Okay, now prompt count C with rubbish. If I print rubbish, then it's not going to read the integer, so it's failed the condition, so it's come up with the usage statement. This is all my program is doing. The system's not doing anything here, it's all programmed. And then finally I do the right thing, count C 10, and it counts to 10. Okay, the fprintf was a print to standard error. I hope. Yeah, fprintf standard error. Okay, in a nutshell, there's standard in, standard out. It's a really clean program. You see how things are read, you see what you do when you can't read it, all command line stuff, of course. standard in, it's not standard out, but it's command line in. Then you see the program working. A scanf is used instead of scanf. I'm just going through all that again. Okay, now that's command line. Now standard input, and we have to change it slightly. Instead of using scanf, which read from a string, the string we had before was the command line strings, depending how many arguments you've got. We're now going to read from a file. But you don't open the file, standard in is the file. So you just need a scanf. So here's our little program that does it now. Identical to the previous one, but it's reading real standard in. File on the operating system. File in the file system. If scanf %d address num is not equal to 1, got a problem. Okay, and there's the problem. It's saying, here's the usage, I want a number. Is what it's coming back with. The rest of the program is exactly the same. I just loop through that number that I've read to prove that I have read it, and it's doing the same thing. Okay, and the usage message this time is simpler than the command line version because we don't have to declare any argv, argc. Notice it's a main void. Argc, argv disappeared here. Don't have to process any strings. It's just give me a number. The Unix program in C can ask give me a number, which is what that scanf does, and it's got to be provided by the system in a sense, or you as a user, by redirecting I/O, by using the less than sign to bring in the input from a file, for example, or to use a pipe command on the instruction line. So now, if I run it, DCC, generating count S, this time, I called it, and I run it /count S without any arguments, and it will sit there forever waiting for you, and I type in 10, it will come back with the count to 10. Okay, the standard input is the screen, it's basically waiting for, the standard input is the keyboard, and it will print the numbers from 1 to 10 on the screen, standard out, default. Now, you say, well, why would I do that? Well, it's because you can redirect I/O. So, for example, input.text has the contents 10, 10, new line, then /count S less than input.text will read that number 10, sorry, the two characters 10 from the file, convert it into an integer, and do a count to that integer 10. And you can do pipe instructions too. A pipe command joins the standard of output of one program to a standard in of another. I thought, well, what the hell? I wrote a quick little program, a few lines, which just does a printf. Void, main void, printf 10, exit. You can write your own little program in a few seconds, a couple of minutes, just prints 10, because I don't want to put it into a file, I want it to generate it. Active rather than passive. And I compile my write 10, I recompile my count S, well recompile, I didn't have to, just wanted to show you the whole lot. The count S has not changed, it's just read standard in. Count S, write 10, writes the standard error, writes the standard out, because it writes 10, printf 10, full stop, end of story. Now I can pipe the two. Pipe the out to the in. Pipe the write to the standard in reading program count S. And you see the 10 disappears. There's no 10. You don't type in 10, so it doesn't get echoed on the screen. It's generated by a program, printf, and it doesn't go to you as on the screen, sitting there waiting, where is it? Which it does do if you just type in /write 10, comes to you. The screen is standard out. If you write that little program and you pipe it to count S is the output. Count S is standard out, not the screen. Okay, so every print statement, if my little write program wrote War and Peace, the whole book, the whole volume, then all of that goes to printf. All of that is printed and goes to count S. Okay? Printf goes to standard out, and when you pipe it, standard out becomes the pipe. So it disappears from sight and goes to count S, which hopefully can do something with it. Some people prefer to use, I just added this as a result of, Rachel, you here? I couldn't see you there. Yes, I thought, well, I'll put it in, because there's still a lot of questions about reading and writing. I can't help but walk around this little, roughly one leash away from the podium here. I've written just in a few minutes this afternoon, getchar. I rarely use getchar, but I have used it in the assignment. And what I've done here just showed you just a tiny little getchar program, which I've called echo standard in. Echo standard in, accosted in, sort of funny word. And that program does a loop. It reads a character from standard in and prints it. Not hard to follow, very simple little program that eventually generates exit success when it reads a new line. Now that little program, you can run it, DCC accosted in, and when you compile it, it compiles, and then you can echo the string born free. Why that came to my head at that moment, I don't know. Maybe because I'd seen The Last Student, and all of a sudden I felt free. So echo born free to accosted in, the executable, and it came back with born free, because all that accosted in does, take it out, is print the echo, or print the statement it's got from standard in. It's an echoer. Okay, so I'm running my own echo program. And here you see I've just run accosted in on its own, prompt /a.out, and I've had to type in BORNFREE. Because it sits there forever waiting, come on, waiting, and normally standard in is the screen, the keyboard. So I type in born free, hit return. If I don't hit return, it'll continue waiting because it's waiting for that return. The moment I hit return, it's into action and everything will come out. Okay, and so it comes out with the born free string. Okay, that little program works a treat. Okay, there's not much. Okay, you can do a lot of things with something like that. Because in a sense it's so simple. It reads one character at a time. Now, without trying to push you down the track on the assignment, it is true that this program can work because there is no storage problem. I'm not storing the string, I'm storing a character, C. The fact that I've declared char C means I've got a little spot in this massive memory where my character is going to be stored. If I wanted to store the whole string, I must malloc. You must malloc too. How much you have to malloc is what the difficulty factor is. What makes I think it makes the assignment interesting. If you're nowhere near that level of arrayless programming, then don't worry about it for the first period. Time is marching on. I'm trying to now encourage you to at least get to a point where you've got a working program, even if it's got arrays in it. Okay, you can get rid of them later. So I don't want to push you down that track of what will I do with my characters, because I want to store all my tile numbers, 1, 2, 3, even the B. What do you do with the B? What do I do with the storage problem? And you've got a malloc, and how much can I malloc? Because I don't know how much I need? Well, malloc 100 and leave it at that. Or malloc 81, 9 by 9 board. Or 11 by 11, malloc something. And just say, okay, that's enough. I'm going to do it with that limited malloc at least. And you may, and you can still, if you're not so much good enough, but if you work out a little bit looking at my programs, you'll see that arrays are just pointers. And it's not much work to get rid of all the square brackets. Because I showed you on an earlier program how with indexing, instead of going the name of the array Fred, square bracket I, square bracket close, you can say Fred plus I. Showed you that in one program. Now that is useful because with an offset, an addition, you can actually get to indexes in your board. Okay, so straight away you say, oh, the malloc, I have a starting point just with an addition of an integer, I can actually get to the array elements. I think I know what to do. Even if you think that now, don't do it just yet. Just get the arrays in there, get something working, do the parity checker, and get some input read. And then worry about how you get rid of the arrays. Okay. Now I'm putting in the user prompt for the Microsofty people. Here's count S plus, count S minus, depending on the way you see this. And I'm asking, please input a number. Very politely, always please. Okay, and the rest of the program's the same. And the scanf, which reads the number, will stand it in. Normally the keyboard is standard in, so I type in 10, or 100, or 1,000, and the program works fine. This line has been added to counts.c. So when I run it, counts plus, that's the name, it says please input a number, and I type in 10, and I'm Microsoft happy. That's the way life is supposed to be. It prints the user prompt, the user types in 10, and the program then outputs the count to 10. If instead you use a pipe as input, then it goes a bit funny. Echo 10 to the executable counts, and what do you get? Please input a number, and there's the string, there's the count, or the count to 10. Everything's sort of going. I didn't want the input string, the prompt in that case, Mr. Computer. I just wanted it when I run it normally. So the prompting doesn't sort of work with prompting of the user. So you can see here, well, the problem is a little bit what is standard in and what's standard out, and it all changes. It gets a bit funny when you use pipes because it redefines things like screens and keyboards, and it gets all a bit wonky. So that doesn't look very good. It's just sort of messed up. So user prompts are not used often in Unix because the Unix way is to use command line arguments that tend to replace them, and it doesn't fit well into the standard input, standard output framework as we see above. Okay? It's not wrong by any means. And if you can live with, and you say, look, I never want to do a pipe, forget it. And in complicated programs, obviously, if you're getting the particulars of somebody, the name, the birth, the date of birth, where they live, street number, all that stuff, you're not going to put that on a command line. Okay, with forms, input of data, real data entry, there's no command line stuff here. We're talking about command lines, not data entry. So in terms of command lines, the Unix way is command line arguments, not questions or statements to the user to do something. It's just the usual Unix way of doing things. A program can open and close and read and write files. This is generally done when you have large volumes of data or complex data, structs, for example, and binary data, stuff you can't read. Obviously, that kinds of things, big data, you probably don't want to have a simple file. You probably need more files to do certain kinds of data, and you've got to bring them together and do something. That's a different game. It's not really a data structures and algorithms course. It's more a database course. But here's a program I thought, I'll do it all in one hit for you. to read a number from a file, input.txt, and to write a count from 1 to num to the file fout, output, out, I've called it there. Good boy that I am, I have a hash defined in and out, so that the file names I just mentioned once at the top, and it's easy to maintain. So, no command line argument, there's a void on line 13. I define my two file pointers, FPI, FPO. File pointers, FPI, FPO, are given the type file. That's actually a stream of characters, by the way. A file is defined as a stream of characters, but that doesn't matter. It's an actual type in C. And I've got an array which is going to be the number of digits in the number that I've put in my file, the input file. I remember I read a string, and I've got to do something with that string. I want to put it into, I have to read that string, and then I convert it to a number. So here you see, now this is the problem with file I/O. There's so much housekeeping. If you read, does it exist? If it doesn't exist, print an error. If it does exist, then go to the next step. So straight away, level 1 nesting. If you've got the file and the information and you want a second file, then you do it all again and you go through another level of another indentation. If you've got to write to an output file, is the output file there or got to be created? If it's already there, maybe you can't override it, so you've got to check that. And if it's not there and you can create it, can you create it? Is the file system full? If it's not full, if it is full, you've got to get out. If it is, straight away, all these if else, indentations, it just gets... And there's nothing to do with anything except housekeeping to make sure your program can run. Because you as a programmer will always do the worst, must take into account the worst case. File system's full and there's no input file. And your program has got to work. It's got to be robust. Your file's not there and the whole file system's completely full. And your program's got to run and do something intelligent, which means terminate as gracefully as you possibly can. Okay, so here's my fopen. If it does open, then I go to my else. If it's null, that's an important check. Can't open file, sorry, return exit failure. Else, then I can read my num, hopefully. Here's my scanf, trying to read my num from the file. Now it's at scanf, not an scanf, I'm now reading from the file, not a string. This unit sort of makes sense. When you see it enough, it sort of, there's a mindset behind it. So it's an fscanf. Remember you saw an scanf, you saw an fprintf, or I mentioned fprintf for standard error. You put the f in front and the first argument's got to be an f, which is a file pointer. So, our first argument is a file pointer. Where are we? fopen out. So I'm now reading, I'm reading FPI, so I've got to read the number first. So I read my number, 10 or 100 or 1,000, whatever it is, and if I can't find the number, it's just a string born free, well, there's no number there, therefore it's going to fail. So in that case, I return exit failure. So the file's got to be there, there's got to be a number. Now, finally, I've got my number, if it's worked, and in the else on line 28, I can close the input file. That's the other thing you've got to do. Don't forget to close your files. Not that it makes much difference, because the system will close them honestly for you when your program crashes or terminates in any way. But it's neater. You don't leave files hanging. It's just very, very sloppy. So you can close something, then close it. So I've closed it immediately. I've got my number, I close the input file, and I open my output. But can I open my output? So here I go into my output. If PO is null, file system is probably full, exit failure. Okay, now if I can open my output, I'm now here on line 36. I've got an input file, I can read my input file, it's got a number in it, and I can write to an output file. It's all possible. All those ifs have happened. Now I actually fprint, fdo, %s. Oh, I'm printing a string FPO, that string, and the string I'm printing is counts. Giving it a heading. Bit Microsoft, giving it a heading so that people know what the numbers mean, the reader. And from 1 to num, the number I've read, finally, this is the real heart of the program. This is what I've done it all for, is I do an sprintf of that number, and I do an fprintf of, why am I doing that? Oh, I'm putting it into S, and I'm putting the string. I don't want to write what was an I straight off into my file, and I'm going to have a non-ASCII thing, and if I ever try to look at that file, it's going to be unreadable. Okay, so I've got to write a string, a character in ASCII form, and that's something you more than likely will forget when you first program. So I've got to write something which is readable to the human, and that is an ASCII string. So I'm converting it to a string, and now I'm writing it. And now I'm closing the beast, and I'm saying I've done it, all very friendly. Okay, and all the error messages go to standard error. The file that's created goes to standard out. That's when it's worked. Read is done using fscanf and write using fprintf, and as it is written, the user must know, of course, the user can't see when it runs that these files have got to be there or not there. The user has no idea. There's no warning to say, have you got your file ready? Or has your file got a number in it? Or is the file name that I've chosen in the program okay? None of that. It's all underwater, behind the scenes, under the bonnet, which is a bit frightening, because you don't really know when you run a program like this, what's it going to do to your files? Is it going to overwrite some important information just because it's got the wrong file name? If you create a data file input.txt that contains the string 13, then you compile and execute the program, DCC files, that's the name of my program, /a.out, file, output.txt is created, so it's worked, and it's come back with a message to say it's finished. I felt the need to at least come up with some message that it's worked, that it's done something. This is that thing, normally in Unix, if no news is good news, style of Unix. Doesn't say anything, there's no error. It's worked. If it tells you anything, it's almost always bad news. The only news is bad news. That's sort of the Unix way. Saying that something's worked is a bit unusual. But in this case, because there are files involved, I think, well, all these things are happening behind the scenes, I better say something, because otherwise you won't have a clue what's going on. At least it's saying that it's happy. I could have also come back with, I'm happy. So the programs are obviously working, that's great. If it was saying absolutely nothing, I don't think I'd be a bit nervous. I would be a bit nervous about what it's done, knowing that it's mucked around with files. So, files created, and then I look at the output.txt, remember, right at the top there, out was output.txt. That was my hash defined. And I just checked to see what's in there, and sure enough, the count from 1 to 13. So it's all worked. But it all worked under the bonnet, underwater. I couldn't see it, and it makes me nervous. If you input text that doesn't exist, so for example, if I ran it without a file being there, if I took the input text away, then it says, because of my checking, it says input file can't be opened, can't open input file. And it is for the user to figure out what this means. So if you run it and you get that, and you think, well, I wonder what that means. And of course, as a user, what would you know? So you've got to make sure you've got the structure around it for files to be there when they're supposed to be there. You can't expect the user to go chasing it up. He has no idea what these files are about, but I suppose you could say that's a bit like what's standard in if it's just waiting for input. What's it waiting for? Same problem. File I/O requires care in programming, more housekeeping, it's more difficult to maintain. You need to have good reason to use files instead of using standard in, standard out. That's the bottom line for me. Program output, we've already seen quite a lot of that because you've been using printfs for a while now. Both are normally the screen. You can't tell the difference normally because you don't check for the difference, but you can if you want to, very easily tell the difference. And the general form for the print statement, I said at the start, was fprintf with some kind of string file pointer. And normally it's sd2, standard out. The string can be standard out, standard error, or can be some user-defined program file, which is what you just saw in the file program. Don't think there's anything. Note the systematic naming. Standard input is scanf, just scanf, the simplest form. If you read from a string, then use scanf, and then the first argument is a string. Standard output is printf, basic form, and if you want to do something special, use a string, then use fprintf. Scan ss and fprintf are the two normal ways of communicating with the operating system. Like standard in, we can redirect standard out, so when I ran that count program and it counted to 10, I can redirect it output.txt. And if you remember that count s wanted to know the number, I still type the number in 10, but the output I don't see. The count from 1, 2, 3 up to 10 goes to the standard out, the redirected standard out, which is in this case output.txt. And of course we can redirect both standard in and standard out. This is where it gets a lot more fun. These command lines can be a lot of fun to put together, and particularly with pipes and redirections. And you can see there the count S has got a redirected standard in, it's input.txt, redirected standard out is output.txt, and the last echo is, well, the standard in is coming from echo, that's giving a string to count S, and the standard out of count S is output.txt. Okay, so you can play with them on the command line. The vast majority of programs can be written using just these library calls: scanf, scanf, printf, fprintf. Fprintf you need for standard error, printf you need for standard out, scanf to read from the command line, and scanf to read from standard in. They're your bread and butter. These should keep you satisfied in life. Okay, you don't really need a lot more. If you do a lot more complex things, then the question is whether you need that complexity. Okay, so that covers standard in, standard out, standard error. The one, not one, there's many unresolved things. There is an issue about what is standard error. What is an error in a program? If a program runs out of memory, runs out of file system space, there's no question that is a real serious error. That's a library call error. Can't open a file, can't close a file, can't do something which is just not your fault. So that has to be standard error. But when the program does something, picks up some wrong data, is it an error, or is it just a feature, if you like, of the program picking up some information that's wrong and that the user has to correct? If it's expecting a number and it comes back with a character, is that an error as such, or is it just something that the user needs to change to get it to work the way it wants to work, in a sense? It's sometimes very vague or unclear what's an error and what is it's just abnormal program behavior. So what is an error and what is abnormal? And presumably everything that is so-called normal is what printf would get a printf. So what deserves an fprintf? There's no rule in Unix, unfortunately. There's a lot of inconsistency. I prefer, to be honest, I prefer serious errors to go to standard error and the rest go just printf. Pick up printf. So, for example, in the assignment, I'm more than happy if you just printf missing tile, no B, 2 tile 1s, whatever. They can go to printf. But some people have an objection to that. They think, well, it's an error. It's wrong. It should be an error. So it goes to standard error. It's okay. When I do the testing, I will be redirecting your standard error anyhow to go to the same file that takes the printf standard out. So standard out, standard error, they're two separate channels. When you run your program, I can force them to go to a file. So I can see the output of your program, whether it be standard error or whether it be standard out. There's no problem for me. The only thing is I would say be consistent. Don't muck around with them and get some standard errors, some printfs. Whatever policy you want, be consistent in that policy. Okay. That's standard in, standard out. And that's finishing that lecture. Now, let's get into the ADT stuff. There's some fun bits in here. Oh, I'm not allowed to look at it. I've got to log in first. Oh, that's interesting. Oh, will it do that? I'm not even sure it will do that. Yep, I'm success. Okay, ADT is a data type. An ADT is just a bunch of operations without data. It's sort of the irony. It's when you go past a data structure that you have, concrete data structure, an array, linked list, in a struct, that you can see that kind of data structure is terribly insecure. If you have a complex program, you want somebody to use a data structure, but you don't want them to change it and do something funny with it, you want it to be protected, then you can't use a concrete data structure. You can't use a normal data structure. You have to hide it. So hiding it is what ADTs are all about. It's putting it into a separate file. Having a bunch of operations where the program operates on the data, and the only thing the user sees are the operations and no data, that is the essence of secure programming. Sophisticated programming, elegant programming is what we strive for. Okay? This is the ultimate structure is hide the data as much as possible in files. C files, of course, program files, not data. In mathematics, they talk about signatures, they don't talk about ADT so much, and the signature here, for example, for a stack, in mathematical terms, would have an operator, would take a couple of arguments and generate another argument. So we have the operator here, for example, to create stack, or to pop and push data, or push data on the stack, or to pop the stack, and to empty the stack. These all take stack arguments. And the result of these all are stacks, except for the pop, which is coming back with an element on the stack. So you here see types. Signatures involve types, and the mapping of input types to outputs. Now in programming, we tend to talk about interfaces, just a .h file, and implementation, the .c file that implements the .h file, and the client, or the program that governs everything, that requires the service, and that is the only thing, we'll call it client. I tend to, all my examples here I've called client in one form or other, so it's very clear who's asking for a service and what the service is provided. And the service that's being provided, defined by the interface, is what makes something an ADT. The ADT can only be accessed through the interface. So the interface is a sort of contract, sits in the middle, it's big in the middle, between the client and the implementation. It's always a very short program, header file. It just says what the pointer is to a data structure, just a pointer. This is where pointers really shine, and it asks or stipulates what the prototypes are of the implementation. The prototypes of the operations in the implementation. The user must know what it can do. It does need to know what the functionality is and what the parameters can be, should be in terms of type of these operators, these functions. So that information, the interface, is very important. So here I've got an example for a client, interface and implementation. I said, well, I've got some kind of implementation, fed ADT.c, of an interface fed adt.h and a client called client.c. That's it, really, in a nutshell, after everything's just playing with C. Why ADTs? Abstraction in the first instance. Hides the data, hides complexity, hides detail, so it can't be corrupted accidentally or deliberately. Very flexible, you can just change an implementation and the user doesn't even know. The client doesn't have to know what's happened in the implementation. It decomposes the problem, and that's what I said, that puzzle is probably arguably on the edge where you really do need something, a couple hundred lines of code. You start to need to have to break it up, although you could probably go a bit further if you wanted to. Structure, it's much easier to read when you know what's being done. The what is the client program, the what is happening here, and the how it has to happen is the ADT, it's the implementation. And the what and the how meet each other at the interface. With the what, it calls the interface, and that gets you to the how. But how it's actually happening, how it's doing your what you want to do, you don't know. And in a sense, you don't want to know. And security means hostility is, you protect from hostility. Here's an example of a point data type. And I define my type def, a struct point, which consists of two floating point numbers. Very simple struct, two floating point numbers next to each other. They should be one underneath each other for the style. And I have two prototypes here, two definitions of operations. I can calculate the distance between the points, and I can move a point, interestingly. And here's my implementation. It's not much bigger than the interface. And you see it includes point.h, which I just showed you. That was the prototype and the type def. And I've also got my two implementations of those two prototypes. And you see the distances, if you remember your Cartesian geometry from school, the float, the dx, is the difference of the x and the difference of y, and take the square root, just Pythagoras' right angle triangle to find the distance between x and y, or xy and xy. Okay, you find that difference in x, the difference in x, difference in y, and you calculate the hypotenuse, which is the square root of the squares. So that's very quick and painless. And the move just changes my point, xy, to a new point that's come in, dx, dy. So I'm adding to a point x, the x that's been pointed to by a, so a is a pointer. So you see that point, a star. A is a pointer to x and y, and it's been changed. Now, that's my ADT. Well, not quite. Of course, look at my client, and my client is being rather nasty, or doing rather unfortunate things. The first thing you notice about the client is r.x, oh, that looks a bit low level. It's changing the struct point, literally changing the fields in the structure. How can it do that? It's not supposed to be able to do that. It's then calculating the distance, setting up my rx, ry, and the ssxy, 2 points with their own x's and y's, calculating the distance between them, prints it, and does that does a move. Okay, it changes the move from -1 plus 2, and then does a recalculation. Okay, so it gives the address of R, changes R, leaves S alone, and does a recalculation to see what the new hypotenuse is, or the new distance is. So, you compile it, DCC point and client point, you run it and it comes back with the two distances. You can check it if you like. Is that an abstract data type? Absolutely not. Why? Because of line 9, 10, 11 and 12, it can change the data structure. Okay, there's no separation here, not properly. It's halfway to an ADT, you could say. There's certain functionality has been moved out, away from the main, in another file, it's this file, point.c, is a separate file. But it's still, the main program is changing a data structure that's in the point.c, which it shouldn't be able to do. So it's boo-boo. So we can rewrite it instead of, now, this line 3 in the point ADT is a bit different. This time, you see, on line 3, typedef struct point star point. Let's go back to what we had before, and we see typedef struct point. No star point. Point is an actual point. If you've got the point, you've got the point. And you can change the point. That is the problem. That's why it's not an ADT. You have to protect the user from the actual data. That means you can't tell them what it looks like. You can't give them the structure. That's what hiding means. You keep it away from them. How you do that in Unix is, and it's the usual question, most questions I ask you in the quiz, if you don't have any clue, just write down a pointer. It's probably going to be the right answer. Because most questions are answered in Unix by using a pointer. So instead of giving them the main program, the client, access to point, as you do here in the interface, in point.h, in pointer.h, we only give the user a pointer to something. He doesn't have a clue what it's pointing to. As far as he's concerned, it's a hidden structure. It could have any kind of structure. It could be a linked list of some bizarre form, or a tree, or a graph, or something. He has no idea. All he knows is it's a pointer to it. And he can change it, or change it in certain ways defined by the operations. So here's our point ADT now. Oh, yeah, point ADT, here's the implementation. I was just a bit confused. I was looking at the client, thinking in my head in the client. Here's the actual ADT, the implementation. Here's our point, our struct point. And, well, the rest is all the same, basically. I'm doing a malloc to create the thing in the first instance. I'm setting it up. I'm doing the distance calculation, which is the same. The move's the same. The only difference, really, is the fact that the internal struct here is just hidden. And the only thing I'm passing to the outside world via point ADT.h is a pointer to this thing, which doesn't tell the client at all what it is, what it looks like, and what they can change. To finish up, here's a client that uses it, same program, but I call create. All I know is that create creates it. So whereas before I specifically had to assign values to my point struct in the client, a real no-no, I've now called a function called create to do it hidden. Obvious. Let the ADT sort it out. It's not for me to do as client. So the ADT creates those 2 points, calculates the distance, moves R, calculates the new distance, and the output's exactly the same. Compiling it is more or less the same, except I've got the ADT on both as suffixes here, but of course they're meaningless. From now on I drop it. I did it for you in the assignment. It suggests that it's important, suggests that it's difficult or something, but it's not. To highlight the fact, from now on, or after the assignment, I'm happy that you drop ADT completely, because everything you should do should be based on this principle of information is hidden, data is hidden from the client. It's sort of the way you style any serious program. 20 line, 30 lines, 100 line programs, obviously not. But complex programs, it's always based on ADT. Okay, and now we've got some mini examples. Stacks are used in real society, moving boxes, stack them up, and you take away the top box. When you have a pile of boxes, you don't take the bottom one out. Wouldn't want to, I would imagine. You start with the top one, and you work back down again, a stack of boxes. Good name, stack of boxes. Putting plates away in the cupboard, you always take the top plate, you don't try and take the bottom plate out. So there's a stack. Putting on more than one pair of socks because it's cold and then taking them off, you're going to have a lot of trouble taking off the first socks that you put on. It's going to be a stack of socks on your feet. Okay, so there are so many things that are stack behaviours that you'd be surprised. And they're all examples of last in, first out. Queues are even more popular, as you would understand, because you hear the word queue, queuing for a bus, queuing in the supermarket, queuing at all sorts of official government organisation offices, lots of places you queue onto a ferry, cars queue onto a ferry, people queue onto the bus. Objects going into a pipe, interestingly, are queued as long as they can't overtake each other in the pipe. First thing in is the first thing out. A pipe is definitely not a stack, okay, unless you've got a lot of fiddling in between in the pipe hidden. Now, a stack, and here's an example of a stack with some operations that you can push something onto a stack. Push 1, push 2, push 3. So the top of the stack is 3, the bottom of the stack is 1, and you could pop off something which is going to be return value of 3, and a push 4, and you'll finish up at that point with 4 to 1 being the stack for top and 1 bottom. We can implement the stack using linked lists, and we probably will go through that exercise shortly and go into linked lists a bit. But for the moment, I'm happy just with arrays. They're much faster to implement and they're far faster to run. Linked lists do have their advantage over it because when you have big arrays, big stacks, then a big array can be a real nuisance in an operating system. It takes a lot of memory. And then when you fragment it, in effect, in a linked list, it's much easier to deal with very large arrays. Not that you'd really want to do that, large stacks. Not that you'd really want to do that, because if you've got this really large stacks, the slowness of a linked list is also a problem. So the bigger the stack, the less likely you are to want to use a linked list because it's just too slow. So it's not easy, and linked lists are rarely a viable option for that reason. There are lots of things you can do with a stack or a queue. You can create the beast, see whether it's empty, or make it empty, see whether it's empty, put data on, take data off, check whether it's empty, get the height, how big is the beast, show me the contents of everything, just get rid of the top of the stack because you won't throw it away. Also, imagination is the only thing that controls how much complexity you want to build into your operations. Normally, to create an ADT for a stack and another ADT, normally we have two stacks, two different data structures, a stack and there's a queue, and 95% of the code is the same. The 5% difference is, of course, one pushes into a different spot than the other. One works off last in, first out, and the other one works off the first in, last out. So it works first in, first out, last in, first out. They're the two. So they work on different ends, kind of thing. So that means, well, all this common code, what I tend to do is I never talk about stacks and queues, I talk about quacks. So here's my quack interface. My quack interface can create a quack and can push something on the quack and can pop something from the quack, can check whether it's empty, can make it empty, and can show me what's on the quack, show the whole contents of the quack. And there's some small details in line 10, return 1 if quack is empty or 0, kind of stuff. Notice I've dropped quack ADT.h. I've just called it quack.h. This is going towards an ADT. What indicates that it's an ADT or helps you convince yourself that it is an ADT? Someone? It's a header file, but everything has a header file. You've got all your definitions always in a header file. It says nothing. No, interfaces don't have implementation. I showed you with point.h an interface, the first one, and it was not an ADT. It had a particular thing in that, a feature, which made it a non-ADT. It's just a data type, because you can muck on. Yeah, the pointer to the struct. It's an excellent question, just to show you, for a quiz kind of thing, the theory kind of thing. Show you that something like that and say, well, what makes that an ADT? Why could that be an ADT? And something else which wouldn't be the pointer, buried in there somewhere, say, do you see that little star there? And do you know what it means? If you understand, oh, that's just a pointer. What good is a pointer to you? Unless you know what the pointer points to, it's meaningless. You can't do a thing with it. You try and print it out, but that's unlikely to tell you anything. So, the Quack implementation, okay, that was just an interface. It's got a lovely pointer to a struct called mode, whatever that is. And here we go to our implementation. And, well, it's all... Okay, the array grows, so we have an array. First element of the array is the bottom of the stack, so it starts at 0, element 0. Push puts an element on the stack, and pop takes it off the stack again. And the array grows as elements are pushed. And, well, straight away we see something interesting, or there's a finite size to this stack. Height, it's the height of the stack. Okay, so there's a limit, and it's an array. It's not an arrayless stack. But after you've done the assignment successfully, if I could say it as brutally as that, you'll say, well, actually, I could easily make an implementation of a stack that's got no arrays in it and make it limitless. They're actually quite not so much common, but it's an often required thing, because stacks, they can go up to the ceiling and they can spend all the time just being 20 or 30 deep, and then all of a sudden you need 500 or 1,000 for just a one-off thing, and it comes back down again. So you don't want a limit on it necessarily at all. And it's hard to say what that limit might be in the worst case. So you try to program it so there is no limit, but this is limited by a height. Can't be bigger. The top of stack is just an index in the array. Underflow occurs when it goes underneath -1. -1 is where it starts. And overflow occurs when it goes above, or it reaches height. Going from 0 to height -1 is the height. So here's the implementation, and now we get into the longish programs. In a sense, this is the first program in the course. That's too much for the slides. But be damned, I'm not going to take them out, because you can still cut and paste and use them. So I don't want to have different sources for the program. The slides are completely self-contained. All the input programs, if I could call them, template programs for you to use, are in the slides. You don't have to look in other places. Okay, so there's my create my quack, and you see I do a malloc of the struct, and then I set my my top pointer to be -1. I push something on the stack by I couldn't see it for a moment. I just wasn't looking. The struct node contains the whole array. I'm just too much in the assignment mode where I got no arrays at all. And I think, where isn't there a pointer? Why is it just giving me a pointer? What's it doing? But the create quack is creating this big array, size, height, and one little number index, top index in the array. Together, you got the big array and that index. Well, you know it starts at 0. You got the index. That's where the top is, and that's it. That's all you need to know. That's the step, and everything operates on that data structure. So I do my malloc of the struct. I can push something onto the struct, the struct, or into the array, onto the stack. As long as it's not null, so it's been set up, I check that it's not overflow, and then I can do it. I increment the top, so the top is the last element. I increment it and write to the array the data that's coming in to push. This is the heart, this is the real soul of the program. Those two lines there, see data going onto the stack. Everything else is sort of admin, housekeeping. This is where it's really happening. Data is going on the stack. Plus, the top, and put an element there. So top is now, from the data structure, pointing to the top element in the stack. And the data's there. Now, pop is the opposite to that, of course. Check that it's initialized, you've got one. Check that there's no underflow. And then, if everything's okay, you return with the top of stack, QS top is what's pointing, or what is the top of stack, the index of the top of stack. That's the element in the array that you want, the index. The top is the index. How do you get to the top? Well, you use this QS, which is my data structure, and it's a pointer. Ooh, get your head around all of this. So then the pointer to a struct as an index to an array, which is being pointed to by the struct. The QS points to array, QS points to top. So there are two pointers going on here. You must understand pointers. They become just so important. So, and then I decrement my top, so I don't really get rid of it. I return it, but it's still there, but the pointer comes, the top comes down, so it's ignored. It's as if it's not there, but actually the data is still there. Now I can make my thing empty if it's, if there is a stack. While it's not empty, I do pops. So I just go through, and as long as it's not empty, I pop everything that's on the stack. So the pop does it all for me. And here's the way I check whether it's empty. If it's empty, well, if there's no stack, if it's empty, less than or equal, if top has reached -1, then it's empty. Otherwise, empty will not be, it will be 0, so you return that. So empty equals 1 is an empty stack. Okay, so when this is true, here's where you're using Booleans to conditions to do arithmetic. With C sometimes it gets flexible. So here we see that condition there, A is less than B. If that's true, then empty is 1. And that's what you return. So if the stack is empty, it will return 1. And if it's not, that's not true, then it's 0, because it was set to 0 here, so it returns 0. It's very sweet, actually, what it's doing. Show quack, and it's going through the whole quack, and I've got the double angle brackets, or double less than sign being to start, and I print all the members of the stack from 0 to top, print ND with a comma after it, and the last print ND, the last one I print here with a closing double bracket. Note I have dropped the ADT suffixes as before, not using them anymore. Here's a picture of it. It's pretty poor from a couple of years ago. I should do that better. I've seen lots of really great pictures of stacks. Create, quack, push and pop, and the height -1 to 0, and the data goes on the first one, etc. Summarising, we have an ADT consisting of quack.h, quack.c. Now, okay, got the ADT, which is worthless until you do something with it. And let's talk about some clients. You can have some fun with some clients. I can see the clock really well now. Okay, a black box tester. I thought it wouldn't be better than having a tester as the first client to see whether the stack is doing the right thing. The quack is doing it. I'm using stack and quack interchangeably at the moment because we are not looking at how we can treat the quack as a queue. We're just using the quack as a stack at the moment. We haven't looked at that problem of what makes a queue really a queue, what's the essence of a queue as against a stack. So at the moment the quack is purely being used as a stack. Here's our black box tester for a quack. Now, I've got asserts in here just to show you I'm not afraid of them. Don't mind using them, but as a tester, okay, this really is debug. I mean, you're not going to ask the user to test his quacks or stacks. This is obviously something only a serious programmer would do. So I don't mind using an assert in this context to show you how it could be used. So I've got my assert.h, I've got my interface quack.h, and I got now, this is an older version. I can see already I'm going to have a problem. I thought I changed that. That surprises me. Quack S is made null, and I've got a second quack T. 2 data types, 2 variables with type quack. Now my first test, I want to create it, and I assert that it's empty. Okay, and I print past if it gets through that. Okay, so I'm calling the cert, and if it gets through that, I print pass the test. Because you know an assert crashes if it fails. So assert is quite useful if you want it to crash. It's not really, not nice. Do you know why it's not nice? If that program with loops and complexity did 400,000 tests on a piece of software, and I use an assert statement, and that program does all these tests, and the very first test is an assert and it bombs out, the other 399,998 tests, or 99 tests, won't happen. So the last thing I do is return on run the benchmark or run the test. I go home, I come back the next morning, and it's done one test and it's failed it. Oh, bloody hell, stupid system. I wanted to, what about the other 300? I could have at least tried some of them, at least tell me what's going on. And you square and fume at the stupid computer, and because you're using an assert, which is just so vicious, you really want to say, well, it failed, next test. Failed, next test, passed. So you want to know. You don't want this, really. But okay, this is the way we're doing it. If it fails a test, it fails, full stop, end of program. So test 2, we push, stack is not empty. Can we push a 1 onto the stack, assert that it's not empty now, and if it does that all successfully, then we've got a passed. We can print passed. Push again, pop twice, then it better be empty. So I pushed 2 on the stack, I pushed 1 before, I pop both off, and I assert it's now empty. Okay, is my stack working? I'm testing it without knowing how it's implemented. It could be implemented as a linked list. I don't know. All I know is I can push and I can pop, and are they doing the right thing and I'm getting the right thing back? Is it really a stack or is it a queue? Well, that's a good question. I haven't checked that because a queue would do the same, have the same behaviour. I should actually check when I should do a push and then a pop to make sure, 2 pushes and 2 pops to find out what the order is. 1 push and 1 pop from a queue also gives me the same thing back. But 2 pushes and then 2 pops in a queue gives them to me in the other order. That's where the queue and the stack are different. So I haven't checked that. I didn't think of that at the time. Okay, and this last test here on line 28, testing error, can I test for underflow? I've got an empty stack and I now pop it. What happens? Oh, that's a different kind of test. I'm now testing for failure. And they're the more interesting tests because it opens up a can of worms. So, what happens? DCC crack with my black box tester. A dot out, test 1, init stack is empty, passed. I'm pushing that push, stack not empty, passed. Passed, testing error, stack, the crack underflow is what I'm testing for, and sure enough, pop comes back with, the ADT comes back with crack underflow. So I know not to panic, it's what I actually tested for. It's a bit like the expected result. The crack is an abstract structure. The client cannot see how it's been implemented. But the error handling is a problem. It is always a problem. And it is something you will come across. And I don't want to spend too much time on it in this course at all because it has nothing to do with data structures or algorithms as such. It is something which is more software engineering of how you design complex software so that it's maintainable and robust. The problems, the questions you could ask yourself is what does a client do with errors that are returned? So a client gets an error and what's he supposed to do? Not knowing how it's implemented. An error may be meaningless to it. So run out of memory. Oh, I don't know anything about that as a client. Memory, do you need memory? I didn't know that. Maybe it was all on disk. What is a serious error and what is a usage error? How serious is the error? Very difficult to know. Is it fatal? Should it be fatal? Or should you go on? Extremely difficult question to answer. How do you test that every error message is correct? How can you generate error messages? How can you generate an error message? You've got to give it an error situation. Some error situations are very difficult. For example, file system full. What are you going to do? Fill up your file system first and then run your program to make sure it generates that error message? That goes a bit far. Probably don't want to do that. So there are error messages that are near impossible to simulate, to provoke. So error testing is a very difficult problem. One of the problems, and that's why it was a couple of people that said, should a malloc that fails be fatal? Should it be an exit or should it be a return? Ideally, it should be a return. In graceful programming, so couldn't get any memory, but I'll try to keep going. But the reality is, two things, problems with that. One, it can mean that you've got an extra parameter or extra information that's got to go back to the main program, and the main program's got to do something with it. So there's extra coding. And really, has that got anything to do with the problem? No, it's just behavioural thing on the edge. Running out of memory, how often does that happen? Never. So, and why should I make a lot of work out of it in my program? That's point one. What was the other point? I always do that problem when I have 2 points and I talk too long on the first, and I forget what the second is. The first is if you don't want that extra programming effort. The second thing is, quite simply, if you've run out of memory for a malloc, then something pretty seriously has gone wrong. It doesn't happen very often, certainly today. Years ago when we were 16-bit machines, okay. But now, memory is cached and there's all sorts of virtual memories. It just doesn't happen. So, really, if it does happen, something so seriously has gone wrong, there's just no point continuing. You better pull the plug and crash the program, stop the program, just exit, get out. Because there's no way that your program is going to do anything sensible if it's run out of memory. It's a pointless exercise. Okay, so it probably is worth an exit. Running out of memory is very serious. A bit like a full file system. What are you going to do with a full file system? You try to limp along and hopefully that you don't need much room, but you're going to die. So you're probably better off just putting out a proper message and just say, I'm giving up. Okay, so that's to do with seriousness. Okay, that was all a client which did black box testing to a degree. Here's another one which reverses the string. We use a stack. It's a really neat little application where we can use pushers to put data onto the stack, and we can use pop to get them off in the reverse order. Oh, that's obvious if you think about it. You push A, B, C, D, A on the stack, B, C, D, E. You start popping E, D, C, B, A. Obviously, you push, then you pop. You push 5 on, you pop 5 off, you're going to get them in reverse order, free of charge. Just 5 pushes, 5 pops, you've got it. That's all the program does. So reverse the characters in the first command line argument. So if I gave you this in the quiz, the things you look for, command line argument, you say, oh, he wants command line argument, argc argv. Oh, I've got to do a scanf, fscanf on the command line argument v1 or v2, depending on which argument I'm processing, and I've got to check that I've got what have I got to read, a character or a string or something, and how many have I read? The scanf's got to return a number, and I've got to check for that number, and if I haven't got that number, I know I've got to bomb out, and if I have got that number, I go on. I think that should be automatic. Command line argument should trigger sort of a way of thinking, or a way of doing. So, I've got a command line argument argc argv, I've checked that I've got it, I've got to check your argc. If I see argc argv at the top and I don't see an argc check anywhere, fail. Easy. I don't even have to look at the rest of the program. You don't check your argc, you've got a real problem. There's no way. I mean, I can segfault that program just by typing in a.out return. Okay? If you're not checking your argc and you don't pick up that there's no argument, and I ask you for command line arguments, and they're not optional, I say it's got to be there, then your program will segfault. The whole memory will presumably generate a core dump. So here is my little program. My input string is this argv1, and I'm defining here char star input, and I'm processing them one character at a time, so I call the input character input C. So char star, it's a pointer. Input v1. And I create my quack, and while I haven't got to the end of the string. The command line arguments are really nice. They're all null terminated for you, guaranteed. It's part of the language. So you can keep reading the command line arguments till you get to the null. And every single one, I do a push, all the characters. A, B, C, A goes on, B goes on, C goes on. 1, 2, 3, 1 goes on, 2 goes on, 3 goes on. 1, 2, 3, 1, 2, 3, A, B, C, they just go on as characters. So when it's, okay, so you do that till you get to the null, and then you reverse. So as long as you get to the null at the end of the string, and when you reverse while you're working on the stack, and you wait to, you pop until you get to the empty stack. Really sweet little program. argc, argv, beautiful. Stack, work down, pop to stack, beautiful, really clean. It actually does something. You can see it working. And prompt, DCC, quack, and reverse arg. I didn't call it that there, did I? Did I change it? No, I did. Reverse arg. Should give it a slightly different name, I think, given it's not just rev arg, which could have been written 1,000 other ways. This is rev arg for with a quack in mind. So dot out. Well, I thought of you immediately. My string is stressed, and it comes back with desserts. Okay, so sort of easy to remember. Okay, client 3. Oh, this is a bit of a boring one. I'm sorry I have to do this to you, but okay. It brings into a new dimension rather than the simplistic, just reverse something. You can do a lot more with these quacks. Given an expression, now you have, just to remind you, infix, prefix, postfix notations. What they mean, infix is, of course, you've got the operator between the arguments, the operands, and then you've got prefix notation where you've got the operator and then the argument, so star AB is A times B. And the postfix, of course, is where you've got the A, the B, then the operator. A, B plus, add the two arguments. Now, postfix is perfect for this because if you think about what you do with a stack, you want to put an element on the stack, an argument, an operand, you want to put another operand, and then you want to operate on the two things on the stack. So, putting the arguments, the operands on the stack, and having an operator at that point in time where you have to operate on them is perfect. Stack, quack, lends itself to postfix notation, also called reverse Polish. So here we have our little program which is going to be called eval postfix, and the string it's going to process is 213 plus 25 star star 7 plus star. So you can sort of say, well, 2's going in the stack, 1's going in the stack, 3. The plus will operate on the 1 and the 3, so that's 1 plus 3. Then 2 goes on the stack. Then 5, then a star. So the star will be 2 times 5. So if I use brackets, then you can say the 1 and the 3 have got to be added. The 2 and 5 have got to be multiplied. Now, you see it all building up, and this one putting your parentheses in, you see what the priority should be. It's pretty horrible. It's almost unreadable. It's hard to actually read that and have any idea what it's going to come up with. When you put all the brackets in, you can see that, well, the answer is 94. How do you program that? Well, the idea is when we get an operator character, whenever we get an operator, whatever's on the stack, the top two elements, we operate on. That's the essence, that's the heart of our solution. And whenever we get an operand, we just put them on the stack. So you get a 2, put it on the stack. Get a 5, put it on the stack. Get a 10, put it on the stack. Everything goes on the stack. It's only when we get an operator, then we take things off the stack. The other half of the coin, side of the coin, is when we have an operator, we take two things off the stack, we operate on them, but we have a result, we've got to put that back on the stack. That's it. You understand that? The program is just the implementation of it. This is where you're thinking and you're playing with the idea. Oh, you understand the principle. Operator, assuming we're talking about a two-operand operator, multiply and addition, subtraction. Take the two elements off the stack, do the operation, put the result back on. Only operands go on the stack. The operators take things off and put things back on again. Okay, so use pop and push, only as computational vehicles, mechanisms, things. The operands are the workhorses, and they get put onto the stack. The operators don't do that. They are workhorses. They do things. So they're the active things. There's one little wrinkle here, and that is that you may have to put on the stack a number bigger than 9. 2-digit, 3-digit, 4-digit, 5-digit, 100 digits. Big numbers can go on the stack. Now they've got to go on as numbers, because we're going to operate them on them as numbers. In that string, that input string, whoops, wrong way. You saw, I shouldn't have, well, it was deliberate in a sense. I should have actually put another example. Well, what happens if you get the number 1, 2, 3 times 4, 5, 6? Or sorry, 1, 2, 3 space 4, 5, 6 plus 1, 2, 3. That's a string. 1, 2, and 3. It's got to read that. It's a string. It's reading a string. So it's got to parse the 1, 2, 3. It's a bit like in the assignment when you get a tile, which is number 10. So not a 3 by 3, but a 4 by 4. You're going to get a bigger, you're going to get a 2-digit number. And bigger tiles, obviously they've got 3-digit, 4 digits. In principle, unlimited number of digits. So you've got to process these digits, these characters, and make them numbers. And that's what you'll see happening here, and that's one of the reasons I did it. Now here's the main program. This is the client. Not touching Quack. Quack is Quack. Quack is quiet Quack on the background. The big main program does the work, and this is going to be our postfix calculator. And you can see I'm here, I've initialized my Quack, create Quack. My input C is argv1, just like I did before. Sort of a style that I have. Command lines are nice. The thing about a command line is they're always the same. They're always a string of characters. You can always do the same thing. So you don't even have to think. You not only can write down argc, argv, you just got to know how many there are, whether they're optional or not, so you've got to muck around with the argc in a condition. But you can always say, when you've got argument 1 or 2 or 3 or 4, whichever one is going to be parsed, that you need a pointer, char pointer to it. So, and that'll be argv of 1 or 2 or whichever argument it is. So that line there, line 17, is so popular, so common. You could almost write it down automatically without thinking. Okay, so I'm creating my stack. As long as it's not empty, as long as it's not null, okay, I'm still reading characters. This is the easy bit. The command line is the trivial easy bit, non-thinking stuff. Now I switch on what I'm pointing to. The input C is a pointer. So star, that is the character. What is it? Is it a digit or is it an operator? Is it a number? Is it an operand or is it an operator? So you see here the plus char, oh good old you are, but you are a good boy, hash define star and plus as hash defines. Probably being a bit too serious, but okay, it shows my heart's in the right place. So plus char is my character, and when I got a char, an operator, I pop, pop, push. We know this. Trivial. Pop, pop, push. Pop the top element of the stack. Pop the second top element of the stack. And push the result, where the result is simply their addition when it's a plus. Do the same kind of thing for a star. This is trivial. You could have done this at school years ago. This is so easy. So really, that should not tax your brain. And you see this one, I love case switch statements with cases. I love them. But they're forbidden by the style rule. Silly style. I like them. And I think it's just so easy to read. If you put if then else around all of this, it becomes a lot of code. Now, when you get 0, 1, 2, 3, 4, 5, 6, 7, 8 or 9, you've got a number. I found the operand. I immediately flag it. I don't know what I'm going to do next. I did this a while ago. And now I've got to actually parse those characters, which are numerical. I know they're numerical because I've got the case. That's what the case does. It tells me they're numerical. You can write this in a more fancy way, but I thought I'd keep it really simple. So I've got these 9 different cases that all do the same thing, and I now want to create the number. And the number is simple. It's just the digits, and when you get another digit, you know the last digit was actually 10 bigger than you thought it was. So if I get 1, that's it. I'm finished. If I get 12, well, the 1 is actually 1 times 10. So every time I get another digit, I've got to multiply the sum I already got by 10, and then add the new digit to it. And when I see that there's yet another digit, then I multiply the previous sum by 10, and then add the new digit to it. It just goes round and round in circles until I get something which is not. So as long as I get zeros and nines, I multiply the sum that I've got by 10 and add the digit I've got at the moment. It's not that simple because the digit is a digit. It's a character. It's not a number. I want the number. If it's 5, I want 5. Not 5, it's string 5, I want 5. Numerical 5. I don't want the ASCII of 5, which is what it is. This is when Unix C becomes fun. It lets you play with characters and integers a lot. It sees characters and will mix the modes very easily and happily. So here you see character, what I call character arithmetic. You can play with characters as if they're numbers. So, yeah. You simply take off that digit, 5 or 9, the ASCII representation of 0. Well, the ASCII representation of 0 is, I've forgotten, 42 or 39, I've forgotten, too long ago. So if I take that off, the character pointed to the input C, of course input C is just a pointer, star is the actual character I'm looking at. I take off 0, I know it's a digit because that's the whole case statement business. I just take off 0, the ASCII 0, off the ASCII 5, thank goodness for ASCII, guaranteed it'll be the number 5. It's a neat trick, it's a C trick. It's what C people like doing. It's sort of get a bit of a, makes them feel good. It makes C people feel very good when they do things like this. So there's a nice little loop there where you build your number from a string. I mean, there are many ways of doing it, and you could use scanf and %d, all sorts of things you can do. It's not that simple sometimes because you've got to be careful that you don't go too far, and you can have spaces or tabs and things, other characters coming in, so you've got to be a bit careful. I thought I'd do it from basic principles, the way a hairy-chested C programmer would do it. Somebody who's proud of their roots and really want to show their ability to do it on their own. None of this high-level stuff. Just get back down to basics, which is working with characters and ASCII and integers. No library assistance. Okay, so here's building the sum. Keep on reading, but I actually read too far because the way this stops is if there's no character, if there's a space or something else. So there's no digit. And that's when I've gone too far. I push the sum back on, so this is the whole point. I've got my number. So when I've got my number 1, 2, 3, I've built up my sum. I started with a sum 1, got the 2. Oh, my 1 was a 10. So it's 10 plus 2, which is 12. Oh, I got now a 3, so my 12 was actually 120 plus 3, it's 123. Okay, if I got a 4, 123 was actually 1,230. With the 4, 1,234. That's how it's working. Okay, so that's, and then because I read another character, oh, it's not between 0 and 9, so, well, I better put it back. Okay, so input C minus minus. I've read one too many from the input string. Remember, input C is a pointer, and it's pointing at 9 or 3 or 7, and the next thing is a space, or an X, or anything, and oh my God, what's that? That's not 0 to 9. So the while loop breaks, and the input C goes back one step. It says, well, I'm finished here. This is my number, and that's where I'm at. And then that goes around again, and if that thing that's next is a space or a tab, just break, do nothing, forget it, throw it away, ignore it. So the whole point of this is what you're doing. I'm incrementing. I'm doing my star input C, and I'm reading all my input, the data, in my argv1. And the default is I've got something I'm not supposed to have there. So it's not a digit, so if I get an X or ampersand or an exclamation mark, then it'll break out here with the default that, my God, what are you reading here? Star input C will tell me what the character is, but it's not digit, and it's not an operator that I can accept, which is only a plus or a multiply in this case. Really nice piece of programming.